In this video, we're going to look at applying exponential functions to certain mathematical problems. And the first problem we look at is example 1. So the population count P of a certain bacteria is modeled by the equation P equals AE to the KT, where A and K are constants and T is time in hours. We're told initially the population was observed to be 250,000. Find the value of A. If after 3 hours the population was found to be 650,000, find the value of K. And then lastly, predict the population count after 10 hours. So we'll take a look at the problem. I'll just note the equation we were given. We were told the population P was given by A e to the K T. A and K are constants and T is time in hours. The first piece of information we're told is initially the population was 250,000. So initially means at the beginning, and effectively we can set T equals to 0. So when T is 0, P is 250,000. 250,000, and we put those into the formula for the population. We will end up with 250,000 equals A e to the 0 times T. So A e to the 0 is 1, which gives us A equals 250,000. So that's the first part of this problem. So now we know A equals to 250,000. The second piece of information we were given was that after 3 hours, so we set T, when T equals 3, the population P equals 650,000. And we now need to find K. So we pop in the information we have. So we've got 650,000 equals A, which we know is 250,000, times E to the K times 3. So we can rearrange this. We'll isolate E to the K3 on the left. E to the K, 3 times K must equals 650,000 divided by 250,000. I'll just note that as 65 over 25, and that can simplify down. Now we're looking to solve for the unknown K, which is in the power of this problem. So we will use ln on both sides. So ln e to 3K equals ln 65 over 25. And I'll use my rules of powers, bringing the 3K down. Now I know ln of E is in fact 1, so it leaves me with 3K equals ln 65 over 25. And finally, to solve for K, I'll just divide out by 3. So that gives me K equals ln 65 over 25, all divided by 3. And just pull that up on the calculator because we can decimalize that answer. So we've got ln 65 over 25. And just be careful with your brackets when you're doing this. You just watch what your screen is showing, that you don't make a mistake. So that decimalized value is 0.3185. I'll just make it 3 significant figures, 0.319. So there's the value of K, 3 significant figures. Now the final part of this problem, we need to predict what the population will be. So we're looking to find the population when T is 10. So after 10 years, we can use the model to predict the population, given now that we know A and we know K. So P equals A is 250,000, e to the power of 10 times our k, which we found to be 0.1319. And I'll just bring that up on the calculator to compute that value, and that will be the first example complete. So we have 250,000 times E, which is shift over ln, 10 times, and I'll just pop in answer because the previous answer is exact, and it was the value of k that we last had on the calculator, so I'll pop that in there. So we get a new, we now have population is 6 million, it's a very large number, it's 6,042,053. So P equals 6042053. That's our final answer for example 1. So we'll move on to the second example. And the second example, we're looking at expressing 3 raised to the power of 2x plus 4 in the form a e to the kx, where a and k are constants. So let's take a look at that problem, and just note first we had 3 raised to the power of 2x plus 4, and we're trying to express that in the form a e to the k times x. So x is the variable in this case, and we're going to use the rules of indices and powers to rearrange the expression on the left until we have an expression that looks similar to the one on the right. So the first thing I'll do is say 3 raised to the power of 2x plus 4 is the same as 3 raised to the power of 2x times 3 raised to the power of 4. And I'm going to leave the right hand side the same, a e to the k times x. Now 3 to the power of 4 is in fact 81, so I'm going to say 81 3 to the power of 2x equals a e to the kx. Now at this point I can assign the value of a equals 81. So we'll just say assume a is 81. If a is 81, then it's true to say that 3 to the power of 2x must equals e to the power of kx. And we're going to again use our rules of ln to find a value of k, and when we have that we can put the expression together in the form that we need. So on the left of 3 to the power of 2x, I'm going to take ln of both sides, ln of 3 to the power of 2x equals ln of e to the kx. Using my rules of powers, I can now say 2x ln 3 equals kx ln e. Now ln e is in fact 1. So I now on the left I have 2x ln 3 equals kx. And I'm interested in finding a constant to represent k. So I can cancel out the x on the left and on the right. So that leaves me with k equals, it's 2 ln 3, or indeed we could say ln 9. 2 ln 3 is the same as ln 3 squared, which is ln 9. So if I wanted to write the expression, putting it all together now, so on my left I would have had, at the beginning I started with 3 to the power of 2x plus 4, and on the right I found a to be 81, and then we'll say e to the power of ln 9 times x. So that that's the example 2 complete. And we'll just look at one final example for this video. And the third example is example 3. The temperature of an oven, T in degrees C, is modeled by the equation T equals 15 plus AE to the minus KT. A and K are constants and T is time in minutes. If the temperature of the oven was 180 degrees when the oven was switched off, find the value of A. After some 20 minutes, the oven temperature was found to be 130 degrees. Find the value of K. And then predict the temperature of the oven after 1 hour. So this example is not dissimilar to the one we had in example 1. But what we'll note is we're dealing with the situation of exponential cooling, which is exponential decrease. So we were given temperature is given by, just minimize that, let's see what's happened there. Okay, so temperature is given by T equals 15 plus AE to the minus KT. That negative shows us it's exponentially declining or decreasing. A and K are constants, as we said. So we're told when T equals 0, this is the time the oven was turned off. When we begin to count the time, T equals 0, time equals 0, temperature equals 180. So we pop that into the equation. We have 15 plus AE to the negative KT equals 180. I'm going to rearrange it. AE to the minus K, and we sub in T equals 0. 180 minus 15 is 165. So we now can say A equals 165. So we have a value of A, and with that value of A, we can use the second piece of information to find the value of K. So when T equals 20 minutes, the oven temperature T was found to be 130 degrees. So pop that into the equation. We have 15 plus A, which we now know is 165. E to the minus K times 20 equals 130. So rearranging again, I have 165 e to the minus 20k equals 130 minus 15 is 115. And I'm going to divide out by the 165. So I've got e to the minus 20k on the left equals 115 divided by 165. And I'm going to, like in the first example, I'm going to take ln of both sides. So ln e to the minus 20k equals ln 115 over 165. And I bring down the minus 20k. Minus 20k equals ln 115. Write that again, you should be careful. Ln 115 over 165. So we divide out by negative 20 and we will have a value for k. Ln 115 over 165 divided by negative 20. And I bring the calculator up to get a value for that. Just clear the screen. We have ln 115 over 165 all divided by -20. So we have a decimalized value here, which I'll maybe show at 3 significant figures. 0.018. Let me just check the calculator again. 181. That's 3 significant figures. Okay, so we now have the values of A and K, and we're ready to predict the oven temperature after 1 hour. So 1 hour, T equals 60 minutes. So we're going to pop in, we are going to put the A and K into the formula. So we now have the temperature equals 15 plus A we said was 165. E to the power of my value of K, 0.0181 times 60. And I calculate that, which will give me a prediction for the temperature, the oven temperature after 1 hour or 60 minutes. So it's 15 plus 165. E is raised to the power of answer times 60. Using answer again because it's the last answer that was on the calculator, so it'll take the exact value. I see my error. I see the error in my way. We have 502. We'd never have an oven temperature of that. So notice I forgot to put the minus in there. So let's go back and delete or edit the expression there. We need minus KT. So with minus KT, we're going to end up with a temperature of just 15 degrees. So after an hour, the oven temperature will be expected to be 15 degrees C. Okay, so that's it for this video, and thank you for watching.